Greetings and welcome to my math channel. Today I have two wonderful problems for you folks. The first problem is actually functional equation, and the second one I'll call it functional inequality. Alright, so the first one is to find all functions from set of real numbers to the set of real numbers such that for every real number x, f of x plus x times f of x is equal to 1. Well, actually, sometimes it's nice to guess some solutions at first, but maybe I don't see any solutions there. Well, maybe you can see them, but no, I can't. So, well, I don't even know what can we start with. Well, for example, let's plug in some simple values like x equals 0. We have f of 0 plus 0 times f of 0 equals 1. Or it's the same as f of 0 is equal to 1. Alright, let's call this 1, this statement. Maybe this did not help us actually. I don't know, what can we do? Maybe... Alright, I know what we can do. Let's assume that there exists such x with x0, which is real number, such that f of x0 is equal to 0. So that is 0 of our function f. Then let's plug it in. When x equals x0, we have f of x0 plus x0 times f of x0 equals 1. Now this is actually 0, and this is also 0, so we have now f of 0 equals 1. And this will be... Alright, let's don't call it by any letter or number, this statement, but we can apply it to our statement number 1, and then we get that f of 1 actually equals 1 in that case. But let's then plug in x equals 1 in our first equation, and then we get f of 1 plus 1 times f of 1 is equal to 1. F of 1, yes, because this f of 1 is just 1, plus f of 1 equals 1, or 1 plus 1 equals 1, and we have contradiction there, so that is impossible. So that means that there is no x0 such that f of x0 is equal to 0, so our function has no zeros. Let's call this statement number 2. Alright, I will rewrite our equation. And maybe we can prove that our function is injective. Yes, so what can we say about injectivity? Let's assume that for some numbers a and b which are not equal, this equality holds. F of a equals f of b. Then in this one, in star, let's plug in at first x equals a and then x equals b, and we have f of a plus af of a equals 1, and f of b plus bf of b equals 1. If f of a equals f of b, then f of a equals f of b, of course. Yes. That is obvious. But then these are the same and these are the same, and that means that a f of a equals b f of b. We have already concluded that our function has no zeros, and therefore f of a equals f of b, and it is not equal to 0, so we can cancel this out, and we just have a is equal to b, which is contradiction. Therefore, our function f is injective. Oh, sorry. Our function f is injective. Alright, so let me remind you something. We have from 1 that f of 0 is equal to 1. Alright, then let's in our equation, let's plug in x equals, x equals f of 0. What do we have now? There is f of 0, yes, plus f of 0 times f of 0 equals 1. This is 1, and this is 1. So we have f of 1 plus f of 0 times 1 is equal to 1. Also, in other words, f of 0 plus f of 1 is equal to 1. And finally, let's plug in x equals 1. What do we have now? f of 1 plus f of 1 is equal to 1. But f of 1 plus f of 1 then equals to, well, this one I can replace by this. And we have f of 0 plus f of 1. F of 1 cancels out. And now we have f of 1 is equal to f of 0. And now we can use this property of our function, that f is injective, and by that, using that, we have f of 1 equals 0. I think you understand. Injectivity is the same as if f of u equals f of v, then u equals v. We just can cancel out these f's if you want. And this gives us that f of 1 equals 0. But that is totally impossible. That is contradiction, because we have proved that f cannot have any zeros. So our final answer will be there are no such functions f. Yes, and that's all. Alright, I hope you liked it, and let's move to the next question. So as I said, it will be inequality, yes, and functional inequality may be more irritating than functional equation, yes. Inequality may be more difficult maybe, but let's see. So again, the function is the same, so from the set of real numbers to the set of real numbers, and we must find all functions f such that for any x, y, and z, which are real numbers, this inequality f of xy plus f of xz is bigger or equal to f of x times f of yz plus 1. So this inequality must hold. What can we do? Of course, we can always plug in some random values, like maybe something really random, like and simple, like x equals 0 actually. What happens in this case? Well, we have then f of 0y plus f of 0z is bigger or equal to f of 0 times f of yz plus 1. Or in other words, 2f of 0 is bigger or equal to f of 0 times f of yz plus 1. And what if we plug in y equals 0 actually? Then we'll get 2f of 0 is bigger or equal than f of 0 whole squared plus 2, well, plus 1, sorry. And that is nice actually, because now we can use our property that actually a squared minus 2a plus 1 is a whole square is a minus 1 squared, and it's not difficult to understand that. Then we have f of 0 whole squared minus 2f of 0 plus 1 must be less than or equal to 0. Or in other words, f of 0 minus 1 whole squared must be less than or equal to 0. But when is the square of some real number is less than or equal to 0? Well, it can only be equal to 0, because for every t, which is real number, we have t squared is bigger than or equal to 0. So it leaves us with f of 0 minus 1 is equal to 0 actually, and which gives us f of 0 equals 1. Alright, that's already nice. That's already pretty much, right? But let's notice that when we just plugged only x equals 0, we had 2f of 0 is bigger or equal to f of 0 times f of yz plus 1. That is a nice equation. Let's just plug in now f of 0 equals 1, and we have 2 is bigger than or equal to f of yz plus 1, or f of yz is less than or equal to 1. Now let's plug in, for example, z equals 1, and now we have f of y is less than or equal to 1. And notice that y can be every number now, literally every number. So this holds for every y. Alright, this will be very important. Maybe let's guess what to do next. Maybe we can do something and we'll prove somehow that maybe f of y actually always is bigger than or equal to 1. Yes, and when we have these both, it is actually the same as f of y is constant, is always equal to 1. Maybe we can somehow prove this. Well, let's try to do that. Let's do the same thing. I'll remind you about our equation, our inequality, sorry. Yes, I'll write it once again because it's lost somewhere. Alright, and then let's plug in x equals y equals z equals 1. This will be helpful also, because then we have f of 1 plus f of 1 is bigger or equal than f of 1 times f of 1 plus 1, or 2f of 1 is bigger than or equal to f of 1 whole squared plus 1. And we have the same square here, so f of 1 minus 1 and whole squared is less than or equal to 0, and that leaves us with f of 1 minus 1 is equal to 0, so f of 1 equals 1. Alright, but now also in this equation, let's actually plug in, well, what can we plug in? Let's plug in z equals 0. Now we have f of xy plus f of 0 is bigger than or equal to f of x times f of 0 plus 1. And notice that f of 0 is actually 1, so these things cancel out, and this thing is actually just 1, so f of x times 1 is just f of x, and we have f of xy is bigger than or equal to f of x. But we also know that f of 1 is equal to 1, so let's plug in x equals 1 here, and we'll get f of y is bigger than or equal to f of 1, which is 1. Yes, actually we proved it. We proved that f of y is bigger or equal to 1 for every real number y, and at the same time it is less than or equal to 1 for every real number. And this is not a question anymore. So if we know that this one holds, then f of y can be only equal to 1 in any point. So f of y is just a constant. F of y is a constant, and actually it is 1. Let's check our solution. F of xy plus f of xz is bigger than or equal to f of x times f of yz plus 1. Now 1 plus 1 is bigger than or equal to 1 times 1 plus 1. And 2 is bigger than or equal to 2. Yeah, that's right. That's true. No, maybe right isn't proper word. Yeah, that's true. And the answer will be f of x is equal to 1 for every real number x. Thank you very much for your attention. Have a nice day and enjoy math.